let's start today's lecture. So today I'm going to discuss some of the examples. I have already introduced several examples last time, but anyhow, let me review from the definition of groups. Okay, today I want to write the definition using some logical symbols. Okay, so G is a set, and the alpha G times G to G, sending a pair xy to xy. Okay, sometimes this part is written as G O plus G. Okay, this is the same thing so far. Okay, and more complicated or advanced mathematics, we want to distinguish these two. Okay, but anyhow, in the beginning, you just assume that these two things are just the same. Okay, there is a group if the following are satisfied. Okay, so G1, this is for all x, for all y, for all z, x, y, z equals x, y, z. Okay, so we read this one as for all. Okay, number 2, there exists E, and for all x, xe equals x equals ex. G3, for all x, there exists x prime such that x prime equals e equals x prime x. Okay. And in addition, G is said to be abelian or an abelian group if G satisfies G4. Okay, right? So last time I wrote in a kind of usual sentence, but today I used logical symbols. Okay, and this one is called this one is read for all, and this one is read as there exists. Okay, so we read from from the beginning. So for all x. So but there's some deletion, and so this we have to say that this x is from G. Okay, this y is from G and yz is from Z. But anyhow, if those things are clear, then we don't write it. Okay, so for all x, for all y, and for all z. Okay, x, y, z equals x, y, z. Okay, and this is associativity. And this one and this one. Okay, this is the existence of identity, and this one is the existence of inverse element. But if you look at these two expressions in logical symbols, a little bit different, right? So the first one starts with for exists and for all, and this one is starting from for all, and then there exists. Okay, these are not interchangeable. Okay, you cannot say change the order. Okay, the first one, the existence of identity element, means that there exists a special particular element to E. Okay, such that for all x in G, this is satisfied. And for this existence of inverse element reads like for all x, okay, this x prime may depend on x, okay, but for all x, there exists some element x prime in G satisfying this. Okay? So, as you know, when we study the examples, this E, for example, in the case of the addition in integers, okay, this E was 0, okay? So this was a kind of special element. And later on, we discussed the uniqueness of the identity element. And we know by theory, okay, identity element is unique. Okay, there is only one identity element. Okay, so this is a kind of special element. But this x prime, okay, which we usually write as x inverse, okay? And sometimes this E is written as 1, okay? Because when we use the multiplicative notation, okay, using the multiplication as notation, okay? So this EX prime is written as X inverse because this is something like X inverse, okay? And this is something like identity 1, okay, if you write the binary operation as multiplication, okay? So sometimes we, instead of writing it as E, we write in the 1, okay? But in the beginning, I think it's better to distinguish the kind of numbers and the elements of groups, okay? So I think in the beginning, I try to use E for identity elements, okay? But as you get used to this type of notation, I may just freely use notation 1, okay, to represent the identity element. And as we recall, okay, for example, the addition of integers, you have this is something now, okay? We have this type of commutativity property. This is called a commutativity. Okay, 可換性. Okay, and so if this commutativity is, say, satisfied for all x and y in G, okay, then the group is called abelian group or abelian. Okay, abelian is taken from the name of the mathematician Abel. Okay, Abel. Okay, but this is kind of small letter, lowercase letter, and the n is kind of conjugated. So then this person becomes very famous. Okay, if it's used as just a capitalized letter and it's just like Abel, okay, then that's the name of a person. But if the ending just changes, and also if you use a lowercase letter, then that person becomes very famous. Okay, but anyhow. So we have this, okay? And last time, I just wanted to discuss one more properties of our groups, but I couldn't do it, so let me do it now. That is lemma 2.1. This is called the generalized associative property. This is page 50. Okay. So this is a little bit long, but this is kind of the English expression, and I just want you to get used to it. So let me write it. Okay. Parenthesis can be inserted or deleted at will without affecting the value of a product. any number of group elements. Okay, that means let x1, x2, x and b elements of a group G if an element U is constructed by combining the n elements in the given order using any mode of bracketing by combining the n elements in the given order. Constructed by combining n elements given order using any mode of bracketing. Then U is equal to x1, x2, x3, xn, so that U is independent of the positioning of the parentheses. This is very long, but anyway, I don't want to write this type of long sentences on blackboard, okay, from now on. But anyway, this is just a practice as you read the textbook, okay? And this one is I just copied from the textbook. Basically, I copied from the textbook. Okay? And from now on, I will just abbreviate the sentence or just write down the say the essence of the statement, okay, which just carries the meaning correctly. But it's also important for you to read through the textbook in order to help you read the textbook. I just copied this part.ちょっとここから日本語でやってみようと思うんだけども、カッコっていう言い方ね、カッコっていうのが3つある、ね、日本語のカッコっていうのの英語での言い方がみんな分かる。ここに2つ出てきてる。何でしょう。ブラケットね。ブラケットっていうのと、ね、ブラケットとパレンテシスっていうのが、それがカッコなのね。パレンテシスとブラケット、ね、それがカッコです。あと他にブレイスっていうのもあるね。だからブレイスとブラケットとパレンテシス。これが大体数学でよく使うカッコです。でみんな小学校でやらないかもしれないけども、小学校とか中学校とか大学校とかやるでしょ、ね、 で、英語の方ではあんまりそういう言い方をしないね。で、ここになってるこれ round parenthesis って言って、まあなんか小括弧だよね。それをまあ同じようにずらっとこう使ったりする round parenthesis ね。それからなんかこういうやつは、こういうやつはこういうスクエアブラケット。あとこういうのはカーリーブラケット。カーリー、僕うまく発音できないけどね。カーリーブラケットとかっていうんだね。それなんかカールしてるでしょ。だからカーリーブラケットって。だから、まあ、その3つをそんなような形で呼びます、ね。つまりこの定理は何かっていうと、そのずらーっと積があるときに過去の付け方によらないで決まるよってことを言ってるんだ。ね。Okay? まあちょっとまた英語に戻ろうね。Okay, so anyhow, the result of the product is independent of the order, say the place we put the parentheses and the sequence. Okay? So, but we cannot change the order of elements. Okay? That is important. Okay? x1, x2, and x2, x1 may be different. Okay? But the place we just put parentheses. Okay? Don't change the resulting element we get as a result. Okay? So for example, if you look at this associativity law, okay, then if you have only 3 elements, these are the only 2 types of parentheses we put. Okay? Because the important part is any operation we are thinking of is a binary operation. Okay? If you have only 2 elements, then we can combine those 2 elements to get a third element. Okay? So we cannot say get the product of 3 elements or so at a time. Okay? Just 2 elements and then some result and then combine with another element. Okay? So that's a result. That's a binary operation. Okay? And so this is the one. We are assuming this much. Okay? But this statement says that we can put parentheses at any place. Okay? And this is the kind of the property we use for free. Okay? From childhood also. Okay? But anyhow, let me prove it. Okay? いいよね。括弧どこにつけてもいい。例えばこう例で言うと ABCD If you have 4 elements, okay, if you have 4 elements, there are many ways to put parentheses, right? For example, say the first one is this type of thing, right? And the other one is A, B, C, and then D, okay? And the other one is A, B, C, D, okay? And then say A, B, C, D, this type of thing, right? So, and also A, B, C, D. 1, 2, 3, 4, 5. There are some more. Okay? But anyhow, this statement says that all these things are equal. Okay? But if you look at this part, okay? If you look at just ABC part, then that is equal to A times BC. Okay? So these two are equal. Okay? And if you look at this and that, okay? If you just think of this BC as one element, then you can put the parenthesis to the other side. You get A times BC. And then this one from here, or I don't know, I don't know how you get this one. Butこれどうやってな、ここだね。If you start from here, okay, you put the parenthesis somewhere here, okay, then you get this one, right? So in that way, if you have only 4 elements, okay, you can put parentheses in any place, okay. But the important thing is you cannot change the order of elements, okay. That is not allowed. Okay? But anyhow, let me prove it, okay. Okay, so we argue by induction on this. Okay, if you is constructed from x1, x2, xn in that order, then u equals b star w, where b is constructed from x1, x2, xi, and w from xi plus 1, xn, with 1i n minus 1 by induction on n, w equals g xn or z equals xn. In each case, u equals y star xn, where y is constructed from x1, x2, xn minus 1, hence by induction u can be expressed in desired form. Okay? Okay. The idea is, for example, in this case, okay, and this 4-letter case, okay, we want to show that everything is equal to this one. This one means first take the first 2 elements, and then combine with third elements, and then fourth elements. Okay, so if all the results, okay, yield this one, then we can show that everything is the same, right? So that's the idea, okay? And we want to use the induction, okay? And there are 2 types of induction, but this one uses a so-called generalized induction, okay? So if, say, shorter form can be reduced to the, say, a normal element, okay, then everything will be fine. We want to show that, okay? Sometimes in high school, you study like a k plus 1 type induction, okay? But we can generalize that type of induction a little bit, okay? That is that we studied in basic concepts in mathematics, but that's not so difficult, okay? So here, I use the kind of the generalized induction, okay? But on my lecture note, I also wrote k plus 1 type induction proof, okay? And I will post that lecture note into the Moodle, okay? If you want to look at some other way of proving this one, please look at it, okay? Read it. But anyhow, let me just think about this one, okay? So we argue by induction n, so we want to prove by induction. If u is constructed from x1 to xn in that order, okay? So order order is the same, okay, but the parenthesis may be put in different way, okay. Then, since this is a binary operation, okay, we are talking about binary operation, the last step has to be a combination of two elements、ね、これ二項演算をやってるんだから一番最後に計算するところがあるわけだ、ね、だから一番最後に計算するところを V と W の積だと考えるわけだ、ね、Okay? In that case, V, we don't know the way we put the parentheses, but the V is constructed from x1 to xi. Okay? And the W part is constructed from xi plus 1 to xn. Okay? Okay, and the I is less than or equal to n minus 1. Okay? Then, by induction, W, so the latter part, okay, the latter part can be written in this way, or Z itself is equal to xn. Okay? Because this W is shorter than n. Okay? The length of, or the elements involved in W is less than, strictly less than n. Okay? Because you have a V part. Okay? So, by induction hypothesis, okay, that is not necessarily n minus 1. Okay? That's a point I just mentioned that this is a generalized induction. Okay? But and also W can be written in this way, okay? Or Z itself is xn, or say W itself is equal to, or I should write W itself is equal to xn. Okay? So that means, okay, even if you have U equals VW, and using the induction, this W part can be written as say, in this way. So, V times and Z star xn, or V times Z xn. Okay? So, you have two cases. Okay? But this one, using, say, associativity, you can write it as this way. Okay? And the V and Z are constructed from x1 to xn minus 1. Okay? Again, by induction, this part together with xn reduced to the product we combine in that order. Okay? And even in this case, it's clear, right? Because the V part is constructed from x1 to xn minus 1, right? So by induction, this V part, we put the parentheses from the beginning, okay? You get the same result. And it combined with xn, you get the same result. So everything is the same. Okay? 大丈夫ね。ここちょっとだけこう式の方の高級なのを使ってるのはここだね。後ろの方の W のところは n-1 とは言えないんだけど n-1 以下の長さになっているからね n-1 以下のところがちゃんとその過程を満たしていれば全体としても OK だというそれが証明できれば OK だっていうそのジェネラライズインダクションってやつを使ってるんだ、ね、原理としては全く一緒だから、ね、だからまあ本当はねこれ僕米国の時も言うんだけどそれを使うのが嫌ならばねこのステートメントを N の場合にそうなるっていうふうに言わないで N 以下の場合に正しいという命題にしておけば N 以下の場合は正しいという命題にしておけばそれを P of N としておけば全くそれだけでそのジェネラライズインダクションなんて言わなくてもできるのねだからまあそういうふうに言えるんだけどまあそろそろジェネラライズインダクションみたいなこともストロングフォームオブインダクションとかも言うんだけどそういうこともちゃんと慣れていった方がいいからまあ、だんだん慣れてくる、ね、そうするとどちらにしてもこの W のパートは it's shorter so you can replace this W by Z part and then xn or this W part itself is equal to xn okay so there are two parts two possibilities okay but in either case okay using induction hypothesis okay of the of the case, the number of elements involved is n minus 1, okay, you can write this part as a product, combining from the beginning. Okay? 大丈夫だね。だからまあこうやってやれば、まあ中学、小学校でよく使ってたことはそのまま正しいということがわかるということです。Okay? So next, since the title of the section example, I want to introduce some of the examples. The first two examples are sort of the one we have already discussed. Okay? The first one is dihedral group of order 2n. Okay? Order 2n means, okay, there are 2n elements. 2n elements. あ、今日ちょっと持ってくるの忘れた。ちょっとSo for example, if n is equal to 4, okay, that is this one, right? So the kind of, sometimes it's called the symmetry group of square, okay? That is, as I explained, okay, this is embedded in a plane, okay? And you remove from the plane and then change it and then put it back to that plane, okay? So the way we can do it is, in this case, there are 8 ways. Okay? Firstly, you can have a kind of rotation. Okay? And the other one is just flip it using the symmetry line. Okay? So that is 1, 2, 3, 4. Okay? There are 4 symmetric axes. So altogether you have 8 possibilities. Okay? You may wonder there may be some other way to do it. Okay? And we will study that type of things more rigorously later. But anyhow, currently just accept it naively that just a rotation and then that type of thing is called reflection. Okay? Using the reflection, you can get all those 8 symmetries. Okay? So for the n case, there are 2n elements in the group. So since this is triangle, okay, in this case there are 6 elements. Okay? So that is the rotation. Okay? And also there are 3 lines. Okay? So by the symmetry, you can get 3 ways to get a symmetry. Okay? And the other one is (2.2 cm). Okay, and sometimes this is written as 2 pi over n. Okay? And this is using radian. Okay, in a textbook they use the degree, okay, but it's just the same thing. It doesn't give you any confusion. So this is just generated by the rotation. Okay, so if this is the case, then rotation is just there are 4 rotations. Okay, including the rotation without moving anything. Okay, so there are 4 ways of rotation. Okay, then we just come to the exercise, which I gave you as a homework. ちょっと宿題のところにちょっと戻ってみましょう。Okay? So, exercise 1.2. Exercise 1.2. Write a complete KD table. Okay? last time I said that it's a multiplicative table, multiplication table. This is same. Okay, this is called a Joseph hill. Okay. Then, okay, so we write, since we, this one, exercise 1.2 is for D3, okay, using this triangle, okay, this triangle. So firstly, you get rotation of 0 degree, okay, and then rotation of 120 degree, okay. I write it down as, say, 2 pi over 3, okay. Then the next one is R 4 pi over 3. This is 240 degree rotation. Okay? And then the vertical, diagonal, and the anti-diagonal. So this is, if you have, okay, vertical, okay, diagonal, and then anti-diagonal. Okay? You can name any other name, okay? But this is just I followed the one similar to the text. Okay, then you have R0, R3, 2 pi over 3, and R4 pi over 3, and V. Okay? Right now I don't want to fill everything, okay? So let's try to find, say, VD. Okay, what is VD? VD は何なんですか? VD. これ何? VD は we apply D first, right? And then V. Right? これ何? 名前が違うわ。2 pi over 3。合ってますか? もうちょっと違うんだよな。合ってる? これ合ってる? あ、D か。GD。Okay, let me just do it over here. Okay, so you have 1, 2, 3, right? VD means BD, right? So that means first D and then D, right? Right? So first D diagonal, so this becomes this. Okay? And then B. So this is clockwise, right? So, but the textbook's notation is anti-clockwise, right? So this is the V R 4 pi over 3. 大丈夫? 大丈夫? Yeah? So this is rotation by 4 pi over 3, anti-clockwise. 大丈夫? だからこれは何かというと BD はこうだから R 4 pi を大丈夫? 大丈夫? もう一度やろうか? 今こうなってるよね. 1, 2, 3. So by first apply D. If you write it in this way, okay, then apply D first. Diagonal. So diagonal is you can get this. So here you get 1, 2, 3. Okay. And then vertical, you get 1, 2, 3. Okay. So 1, 2, 3 goes to this one. Okay. this is just a rotation by 4 pi over 3 anticlockwise. Right? Then let's try the other one, dB. Starting from 1 to 3. 1 to 3. First B, and then diagonal. You get 1, 3, 2. Right? So this is R2 pi over 3. Very good. Okay, so I want to stop here, okay? But the order is important, okay? So if you can get this one, then the rest of them will follow automatically. Okay? So please check your solution and get a correct one. ここまでいいかな? Very good. Okay? But the reason I just checked these two parts is that if you look at exercise 1.3, okay, that one asks that is D3 abelian, right? And this is not abelian, okay, because the result of BD is not equal to DB, right? BD is not equal to DB, so this is not abelian. Okay? But if you combine some other elements, okay, then some of them are commutative. Okay? So if you take, for example, R 2 pi over 3 and R 4 pi over 3 also, okay, they are commutative. Okay? But since some elements, some pair, okay, are not commutative, so this is not abelian. Okay? In order for the group to be abelian, all pairs have to be commutative. いいよね? OK? じゃあね、次はこのあれを皆さん教科書を見ながらちょっとこのなんか目がチラチラするってことはないか、目がチラチラするこの22番を見て、このグループの名前を For each design below determine the symmetry group. イグノはインパーフェクションね、ちょっとやっぱり印刷だからインパーフェクションはありますよね。ちょっとそれはあんまりごちゃごちゃ言わないでねっていうことだけど、determine the symmetry group. Okay, let's do it. Okay, from left up, left top. Okay, top left. Okay, 一番上から I want you to say using these names.Okay, DN or CN. Okay, 左上のはこれ何？誰か？じゃあそっちからいこうか。シグマこれ。今これ見て。はい。それ。ちょっと待って、これはその新しい教科書の。これも番
号だけ違って中身は一緒です。
中身一緒。これね、これはどれ、何答え多分 C4 だね。いい ?C4 って何っていうのは、これはどっかでバタンとこういうふうにリフレクションするんだけど、繰り返すやつはダメだね。重ねられないね。でしょ。だからローテーションしかダメなんだ、ね、で90度のローテーションが OK だから C4 なんだ。いい？分かった？そういう感じでいきたいんだけど大丈夫ですか？で次、菊山さんかな。次はその右。これは D5 だね。いいよ。はい、その次。
D4。
これはどう？ D4 で合ってる？なんか8個ぐらいあるような気がするんだけど、回せるのはまあ9 90度しか回せないし、それごとにこのひっくり返すのも大丈夫だね。だから D4 だね。いいかな。どう吉見さん、その次の右のやつ、これはこれはっていうの C の2だね。C2 だね、これね。いいよね。じゃあその次行こう。その次はちょっと待って、お名前なんだったっけ。今ますのね。これはC の4、どうですか。これそのインパーフェクションはわからないけどひっくり返すやつは大丈夫なんじゃない。裏返しするやつ、この対称軸に従ってバタンと折り返すやつ、ね、そうすると縦と横とダイアゴナルと反対ダイアゴナルのところに対称軸があるから D4 と、ね、D4 のような気がする。いいですか皆さん。いいいい、これは D4 ね。じゃあその次は小玉君かな。小玉君、はい、これは
これも D4。
これ D4 ってその今ね、上から2段目の左から2番目見てるんだよ。ウルマークみたいな
あ、これは C3。
C3 だね。これひっくり返すのなんか良さそうに見えるけどちょっとダメだよね。ね、だから C3 だね。OK、 その次は
D3。
D3 だね。これは D3 でいいよね。真ん中ちっちゃいところも大丈夫だね。変なこと書いてないよね。もう一度こちらから。これはもうちょっと数えるのがいくつあるのこれ何これ D16。 本当？どう大丈夫？ちょっとチラチラしててなんか数えられないんだけどね。まあ僕の答えも D16 って書いてあるわ。D16 ね。OK、 じゃあその次はボトムレフトだね。D7 どう？いいかな？いい？ OK、 the next
D4。
D4、 これも D4 だよね。ちょっともうちょっと行きたい感じがするけどちょっといけないよねでいいよね D4。OK、 その次は
D5。
D5 で良さそうだね。OK、 じゃあその次は今もそこからまたこれ何これ一番右だよ。12345678910個あるんだけど、D と C の区別は何だったっけ？だから D5 か C5 かっていうのの違いは、ひっくり返して重なるかどうかね。だから対称軸が例えばバーティカルの縦の線の対称軸を使ってひっくり返すとこれ向きが違うから反対になっちゃうよね。だからこれは回転はいいんだけどローテーションは OK なんだけど、ね、リフレクションっていうノンシンメトリーはダメなので、これで何これ C のいくつのこれ10のような気がするね。なんか 数えると目がちっちゃいするからなってこと知りてんのような気がします。ね、分かった？ね、そういうふうになってる。これは問題じゃないんだけど、ちょっと一番上の18に書いてる。これ18の何？Determine the symmetry group of the outer shell of the cross section of the human immunodeficiency virus HIV shown below. これは C2? そう。これはまあ C と言うなら C1 というかダメだね。だけど、まあ、これは周りのところに関してだけ言えばちょっと数えられないけど何個あるんだろう。28？ だから C28 とかもしひっくり返してもいいなら D28 みたいになってるんだね。だけど真ん中のところの角のところにこうなんか遺伝子みたいなのが入ってるから、これまで含めちゃうとそういう対称性がないんだ、ね、これ実はそういう生物とか、それからこれは生物だけど物理とかそういうところでもそういう対称性を使うことによって数えるのをとか検査する方法をすごく少なくしちゃったり、あるところでの状態を見るのにこことここは対象だからこちら側のエネルギーとこちら側のエネルギーが同じだっていうようなことをすることでもう極端に計算を少なくしたりとか、そういうことで物理とか科学とか生物でもそれなりに使うの、まあ、実は生物は今まであんまり使ってなかったからだけど最近はそういうモレキュラーバイオロジーみたいなのが発達してきたのでちょっと使うようになって、例えば遺伝子なんかの配列のところのある部分のところを取るとひっくり返しても同じだとか、ね、こういうふうにシャッフルしても同じだとか一部分を取ってたよ。そういうようなところからこれはどこのところのパターンを取ったものかとかっていうことを特定するためにもそういう群問とかを使ったりするのが出てきて、だからまあここの下のこのような絵ばっかりでやってるわけじゃなくて、ただいろんな配列のところでのどれだけのシンメトリーが関係しているかっていうことで使うことっていうのは科学の中ではすごくある。まあいいでしょう。Then let me just move on. I will introduce two very important examples. That is Zn. Okay. So we have already discussed Zn in basic concepts in mathematics. Okay. So Zn plus. Firstly, we consider Zn plus. Okay. Zn is a set of integers up to n minus 1. Okay. N is a positive integer. Okay. N is a positive integer. So for example, Z3, say let me take Z6, is 0 to 5. Okay? And then for AB in Zn, okay, and the A is congruent to B modulo N, if and only B minus A divide, this can read divides. Okay? So that means there exists C in Z such that B minus A is equal to Cn. Okay? So we write A is congruent to B modulo N in this way. Okay? And then, moreover, A is congruent to B modulo N, and C is congruent to D modulo N. Then A plus B is congruent to B plus D. A plus C is is congruent to B plus D modulo n. So if we set A plus B to be the remainder of A plus B divided by n, then A plus B equals A plus B modulo n. Okay. Then A plus B plus C equals A plus B plus C. A plus B plus C. This is equal to A plus B plus C. This is equal to A plus B. So using this operation Gn plus, or we just use plus, okay, plus notation is a group. There are several ways to explain this, but for example, let me just explain by example. Okay, if you have G6, okay, then 0, 1, 2, 3, 4, 5. Okay, and then we are using addition. Okay, addition, and we want to define A plus B as the remainder 上位だね、余りだね。remainder of A plus B divided by N. A plus B を N で割った余りだね。Okay, so for example, 2 plus 4, you get 0. 2 plus 5, you get 1. So 2 plus 3 is 5, 4, 3, 2. Okay. So for example, you get this result. Okay, then with respect to this operation, Gn becomes a group. And okay, if you define A plus B in this way, okay, this remainder part or the result part is uniquely determined. It's just easy to determine. Okay, because if you take A and B, okay, then the result is just a remainder of A plus B divided by N. Okay, so that is uniquely determined. But then you have to show that that satisfies associativity, right? So, but here I use the property that A plus B is congruent to A plus B, okay, using the notation like this, okay? So A and B are congruent, okay? We say N を法として等しい A is congruent to B modulo N, okay? It's defined by this condition. B minus A is divisible by N, or N divides B minus A, okay? Meaning that there exists a C and Z such that B minus A can be written as a product of C and N. Okay? So that this is the definition. Okay? This is the definition of this one, and this is the definition of this one. Okay? And then it's easy to see that this thing holds. Okay? This is easy, okay, if you have this and that. Okay? Then in order to show this, okay, just subtract B plus D. No, A either way, but the A plus C from B plus D also. Okay. Then using these properties, you can also show easily that the difference between the B plus D and the A plus C is divisible by N. Okay. So this holds. Okay. So A plus B plus C, if you take it, then this is equal to that. Okay, using this property. This property you that. Okay. Then this is, since these two numbers are as integer, they are just the same number. Okay, so this is equal to that. Okay, then this is equal to that. Okay? But the resulting number of all, say, less than or equal to n, less than or equal to n minus 1, okay, between 0 and n minus 1. Okay? And this and this are congruent. That means the difference is divisible by n. Okay? That means both of them are at most n minus 1, okay, between 0 and n minus 1. And the difference is divisible by n. Okay? That means this number and this number are equal. Right? So by that, we can claim that that operation satisfies associativity. いい？ちょっとここでもテクニック使ってんだよ。ね？いい？こういうふうに決めちゃうと値は非常に簡単に決まるのね。だって n で割って余りだから。だからそうするとちょっとややこしいことが分かって3つやるとこれとこれやった時とこれとこれやった時とでややこしいのね。だけどまあ先にこっちのことをやっておけばこれが等しいよってことを言っておけばさっき言った僕のエクスプラネーション説明でこれとこれとが等しいということが分かる。これはコングラントのね。コングラントなんだけどこれが等しいよということが分かる。その0とかっていうのはね、それから1っていうのは0っていうのが分かるからこれはグループ。Let me just finish up one more thing. Okay, that is example 2.4. That is un. Okay, so for a positive integer un, again we use the product. Okay, modulo n, and then c equals b modulo n. Then ac equals bd modulo n. Okay, and from this, a times b is the remainder of ab divided by n. Okay, then a times b equals ab. This is just a similar thing. Okay. Then by the similar computation, you can show that the A, B, C. Okay. This becomes a monoid. This becomes a monoid. That means that has an identity element and it satisfies associativity. But it's not a group. But if you let un to be the element A in Gn such that there exists B in Gn such that AB is equal to AB is equal to 1. Okay? Then this becomes a group. Okay? And the explanation of that one is written in this sheet. Okay? So please review this. ということで今日はここまで。Okay? And these two examples are used very often. Okay? So please review these two examples. So I think I distributed the syllabus. So that Wednesday we will have recitation. Recitation means enshu. Okay. So it says volunteer. So anyhow, in the beginning of the class, please come to the blackboard and write. Choose your program and then write it on the blackboard. Okay. You can choose any program.